There is a moment you have lived 1,000 times and never once thought about. Your hand touches something hot, and before you decide anything, before your mind forms a single word, before you even understand what is happening, your hand is already gone, already pulled back, already safe. The thought comes after, the pain comes after, but the movement, that first desperate retreat from fire, that happened without you, something in your body knew before you did. That is not a small thing. That is one of the most important things about you, and it is also one of the oldest. Now consider the opposite. There are people alive today who cannot feel pain. Not people who are brave. Not tape who have learned to endure. People whose nervous systems, from birth, simply do not carry that signal. Pain does not arrive for them. Not ever. For a moment. That sounds like a gift. It is not. Children with this condition bite through their own fingers without realizing it. They walk on broken bones for days. They wake up with infections that have been spreading for a week, because nothing told them to stop, to rest, to protect the wound. Without pain, the body has no way to announce that it is being destroyed. Most of them carry permanent damage by the time they reach adulthood, not because the world was cruel to them, because their own bodies could not warn them when it was. The absence of pain is not freedom. It is silence where an alarm should be ringing. And that alarm, the one your hand obeyed before your brain caught up, is what this story is about. Not about suffering. Not yet. But about where that alarm came from. How old it is. What it cost life to build it. And what happened over hundreds of millions of years, when a simple warning signal became something far heavier than any warning was ever meant to be. Before pain was suffering, it was a message. And before it was a message, it was one of the oldest things a living body ever learned to do. Move away, or be destroyed. Go back far enough, and the world had no emergencies. Not because it was peaceful. The early oceans were not peaceful. Chemistry was violent. Geology was violent. The collision of molecules was constant and indifferent. But violence. In a world with no nervous systems. In a world where nothing could detect that something was going wrong, was simply the background condition of existence. There was no alarm. There was no signal. There was no body that could register the difference between being nourished and being dissolved. There was just chemistry happening. We are talking about a world more than 500 million years ago. The continents would be unrecognizable. The atmosphere would kill you in minutes. And the oceans, the shallow, warm oceans that covered most of the planet, were alive in ways that had been running successfully for billions of years before anything like a nervous system ever existed. In those oceans lived Dickinsonia. If you saw Dickinsonia on the seafloor, you might not immediately know what you were looking at. It is oval, ribbed, segmented, anywhere from a few millimeters to nearly 1.5 meters across, depending on the specimen. It pressed its body against the microbial mat beneath it and absorbed nutrients through its underside. It moved, slowly, leaving traces in the sediment that paleontologists can still read today. It was alive, genuinely, successfully alive. Its kind persisted for millions of years. But Dickinsonia had no system, as far as we can determine, for translating damage into information. If something began dissolving one edge of its body, that fact stayed local. There was no pathway to carry news of it elsewhere. There was no center to receive the news, even if it could travel. The damage would simply continue until it stopped. And Dickinsonia would go on absorbing nutrients through the parts of itself that remained. Not because Dickinsonia was tough, because Dickinsonia had not yet been built with any machinery that could turn damage into experience. This is the thing that is easy to misunderstand about the world before pain. We tend to think of it as a world where creatures suffered, but could not express it. That is not what it was. To suffer, in any meaningful sense, requires a system capable of registering that something is wrong and caring about the answer. Dickinsonia almost certainly had no such system. It did not endure its injuries in silence. It simply had no framework in which its injuries existed as information at all. It may have lived before suffering, not because it was protected from damage, but because life had not yet built the machinery that could turn damage into experience. This distinction matters more than it might seem, because the story of pain is not a story about when life first got hurt. Life was getting hurt from the very beginning. The story of pain is the story of when life first built something capable of knowing it was getting hurt. And then, much later, when that knowing became feeling. And then, later still, when that feeling became something that could outlast the wound that started it. To understand that journey, you need to hold 4 things in your mind as we go. The first is irritability. Even a single cell, with no nervous system, no brain, nothing we would recognize as a sensing organ, can respond to its chemical environment. A bacterium will move away from toxins. This is not pain. This is chemistry, responding to chemistry. A reaction with no experience behind it. No signal being processed. No information being stored. The second is nociception. This is the detection of stimuli that are potentially harmful, paired with a response that moves the organism away from the source. It requires more organization than simple irritability. It requires pathways that can carry a specific kind of signal, dedicated hardware for detecting the kind of damage that threatens survival. But it does not necessarily require consciousness. A body can have nociception and have no inner experience of anything at all. The third is pain, something more. The signal, not just detected but processed, integrated, given weight, allowed to influence the whole organism rather than just triggering a local response. Pain, in this sense, requires a nervous system complex enough for information from one place to matter to the whole. And the fourth is suffering. Pain that enters memory. Pain that generates fear. Pain that a mind can anticipate before it arrives, revisit after it has gone, and carry as a weight that shapes every decision going forward. Suffering requires not just a nervous system, but a self complex enough for the pain to belong to someone. These 4 things are not the same. And the reason that distinction matters is that the history of pain is not a single invention. It is a 400 million year accumulation. A ladder that life climbed slowly, without knowing it was climbing, driven by pressures that had nothing to do with producing anything like human suffering, and everything to do with the simpler and more immediate problem of staying alive long enough to reproduce. Dickinsonia was not on that ladder, but something was about to change that would begin building it. And it would not begin gently. The world was about to start moving, and when things move, they can chase each other. And when things can chase each other, being caught becomes the most important problem a body has ever had to solve. Before a body could say where it hurt, it had to learn to say that it hurt at all. Before that, it had to become a body in a meaningful sense. A single thing rather than a collection of parts. Something where information from one location could matter to every other location. Something where an injury at one end was not just a local problem but a message that traveled. That required an invention. Not an invention in the sense of a sudden insight or a designed solution. An invention in the sense that evolution produces inventions, which is slowly, accidentally, under pressure. When the organisms that happen to have some slight version of a useful thing survive slightly better than the ones who do not, across thousands of generations, until the slight version becomes a real version, and the real version becomes something that shapes everything that comes after. The invention was the neuron. And to understand what the neuron actually did, it helps to understand the problem it solved. A large body, made of many cells, faces a coordination problem that a single cell does not. If you are one cell, every part of you is equally close to every other part. Chemical signals diffuse across you in moments. Your whole self can respond to your whole environment almost simultaneously. But if you are a creature with thousands of cells, or million, the chemistry of one end takes time to reach the other end. A threat that arrives at your front surface does not automatically mobilize your back surface. You are not one thing responding to the world. You are a collection of things, each responding only to what it is immediately touching. The neuron changed this. A neuron is a cell that has evolved to carry electrical signals along its length and to release chemical messages to neighboring cells at the end of that signal. A single neuron can bridge distances that diffusion cannot cross quickly. A chain of neurons can carry information from one end of a body to the other in fractions of a second. And when neurons are connected to each other in a network, something new becomes possible. Not just fast signaling, integrated signaling. The state of one part of the organism can influence the behavior of the whole organism. A disturbance in one location can spread. A response can be coordinated. This is what the nervous system was. At its beginning, not a thinking machine, not a seat of consciousness or a generator of experience. A coordination network. A way for a body to become, in a functional sense, one body. Consider animals like hydra and jellyfish, cnidarians, animals whose nervous architecture gives us a living window into one of the earliest ways a nervous system can organize a body. Hydra has no brain, no central processor, no region that receives all signals and makes decisions. What it has is a nerve net. Neurons distributed across its entire body, connected to each other in a diffuse mesh. When something touches one part of Hydra, the signal does not go to a command center and wait for instructions. It spreads through the net, across the body, and the whole organism responds, contracting, shifting, moving in a coordinated way that no single cell could have produced on its own. This is not pain. Nothing about what Hydra does requires us to believe that Hydra experiences anything. But something is happening here that has never happened before in the history of life. A body is responding to a threat as a unified thing. Information is traveling. A signal that started in one place is changing what happens everywhere else. For the first time, a body could refuse. Not refuse in the way a conscious being refuses. With intention and awareness and a sense of self that decides not to comply. Refuse in the most basic biological sense. The whole organism pulling back. The whole organism mobilizing in response to what happened at its edge. The whole organism doing something different because of something that touched it. That refusal is the first ancestor of pain. Not pain itself. The evidence does not support calling it pain. And the distinction is not pedantic. It matters because the distance between what Hydra does and what you do when you burn your hand is the distance this entire story covers. But what Hydra does is the beginning of the same process, the same logic, the same architecture that, given hundreds of millions of years and an increasingly dangerous world to operate in, would eventually produce something capable of suffering. The nervous system did not begin as a way to feel the world. It began as a way for a body to become one body. And a body that is one body can do something that a collection of cells cannot. It can decide, with its entire self, to move away from what is trying to destroy it. That decision, made without thought, made faster than thought, made by bodies that had no thoughts at all, is the thing your hand did before your mind caught up. It is 500 million years old. It has been refined by every generation of every animal that ever lived long enough to reproduce, and it is running in you right now, continuous and automatic, monitoring the boundaries of your body for anything that crosses the line between the world and you. The line between the world and you. That boundary is something Dickinsonia, in all likelihood, did not have in any functional sense. But the moment a body develops a nervous system capable of responding as a whole, that boundary starts to mean something. There is an inside, there is an outside, and the outside can threaten the inside in ways the inside now has the ability to register. This is not yet a self. It is not yet consciousness. It is not yet pain as we know it. But it is the beginning of the hardware. And the world was about to give that hardware a reason to become something much more sophisticated than any nerve net could handle. For most of the history of life on this planet, the ocean floor was a quiet place, not silent. Chemistry was always happening. Currents moved. Sediment shifted. Microbes processed the world in their slow, patient way. But the quality of that world, the texture of it, was fundamentally passive. Things drifted. Things absorbed. Things grew and died and were broken down and became part of the chemistry that fed the next generation of things that drifted and absorbed. Nothing chased anything. Not in any meaningful sense. Not in the sense that required a body to make a decision in a fraction of a second about which direction to move. Not in the sense that made the difference between fast and slow a matter of survival rather than simply a matter of efficiency. And then, in a window of time that geologists still debate the precise boundaries of, something changed so completely that the ocean was never the same again. Bodies started moving with direction, with what the fossil record, when you learn to read it, can only be described as intention. Not intention in the conscious sense, but the functional equivalent of it. Bodies organized around a front end and a back end. Bodies with sensors pointed forward. Bodies built for the logic of pursuit and escape, which is a logic that requires, above everything else, speed. The Cambrian period, roughly 540 million years ago, is where this story becomes violent. Eyes appeared, not simple light-sensitive patches, but structured eyes capable of forming images. Eyes that could see a body moving across open water from a distance. Eyes that could lock onto a target. Eyes that transformed the ocean from a world where you learned about danger by touching it into a world where danger could find you from across the water before you had any idea it was coming. And when eyes appeared, the mathematics of survival changed permanently. If something can see you from a distance, then the time between detection and contact is no longer zero. There is a gap, and in that gap, everything depends on what your body does. Does it freeze? So does it flee? Does it have the hardware to even register that something is coming before it arrives? This is the world that built the warning system. Not slowly, not gently, under pressure so immediate and so lethal that every generation that survived was the generation that had slightly better, slightly faster, slightly more organized sensory machinery than the generation that did not make it. In Chengjiang, China, there are fossils approximately 520 million years old that have preserved something extraordinary. Not just shells, not just the outlines of bodies, nervous tissue, actual neural architecture, fossilized in such detail that researchers can trace the pathways of ancient nervous systems in animals that have been dead for more than 500 million years. What those fossils show is not primitive. That is the thing that surprises people when they first encounter this research. The nervous systems preserved in Chengjiang are organized. They have differentiated regions. They have structures that process different kinds of information differently. These are not nerve nets distributed evenly across a simple body. These are early versions of centralized nervous systems. Animals that had already begun concentrating their processing hardware in specific locations, building the architecture that would eventually produce brains. This is physical evidence of ancient nervous architecture, not evidence of subjective pain. The fossil record can show us the machinery. It cannot show us what it felt like to be inside it, if it felt like anything at all. But it shows us that the machinery capable of organizing sophisticated sensation had already become complex by the time these animals were alive. And these animals needed that complexity, because the Cambrian Ocean was a world where more bodies were moving, sensing, pursuing, escaping, piercing, and being pierced than at any previous point in the history of life. A world where having slightly faster signal transmission between your sensory organs and your muscles was the difference between escaping and being consumed. A world where a body that could not quickly locate the source of damage, could not quickly determine which direction the threat was coming from, could not quickly mobilize a response that prioritized escape over everything else, was a body that contributed very little to the next generation. Evolution does not design things. It does not sit down with a problem and engineer a solution. But it does something that produces results indistinguishable from design when the selection pressure is strong enough and consistent enough across enough generations. And the selection pressure in the Cambrian Ocean was about as strong and as consistent as it ever gets. What it produced, in nervous system after nervous system, across animal lineage after animal lineage, was increasing specificity. Not just detect. Detect what? Not just respond. Respond how? And how quickly? Not just signal. Signal where the problem is, what kind of problem it is, and how severe. Because a body that knows it is being damaged somewhere is better off than a body that does not know, but a body that knows it is being damaged on its left side, near its rear, by something applying pressure rather than heat, is better off than a body that only knows something is wrong somewhere. The more specific the information, the more precise the response can be. And precision, in a world of pursuit and escape, is survival. This is where the warning system begins to look less like an alarm and more like a language. Not a language with words or grammar or meaning in any way we would recognize, but a language in the functional sense. A system for encoding information, transmitting it, and using it to generate appropriate responses. Different signals for different kinds of damage. Different pathways for different kinds of threat. Different urgencies for different levels of severity. Pain's ancestors did not evolve in peace. They evolved in a world that had begun to bite. And every body that survived the biting carried forward into the next generation the hardware that had helped it survive, a little more organized, a little more specific, a little faster, a little better at turning the raw fact of damage into the kind of actionable information that could keep a body intact long enough to pass its nervous system onto something that would refine it further. This is not yet suffering. We are still far from suffering. But we are no longer in the world of Dickinsonia, absorbing nutrients through a soft underside, while damage that happens at one edge stays local and unannounced. We are in a world where bodies have begun to build the infrastructure of warning, where the fact of being hurt has started to become information, where that information has started to travel through organized pathways to organized processing regions, where, for the first time, a body being damaged in a dangerous world has something it did not have before, a chance to know about it in time to matter. There is a worm you have almost certainly never thought about. It is about 1 millimeter long. It lives in soil and in decaying organic matter. It has no eyes in any useful sense, no ears, no nose. It has exactly 302 neurons. Not approximately, not roughly, 302. In every individual of the species. Mapped completely. Every connection between every neuron documented in full. Its name is Caenorhabditis elegans, and it is one of the most studied organisms in the history of biology. Researchers have spent decades on it, precisely because of that fixed number. If you want to understand what a nervous system does at its most fundamental level, 302 neurons is a tractable problem. You can actually see the whole thing. You can ask, of any behavior, exactly which neurons are involved, which connections are being used, what the signal looks like as it travels, and what C. elegans shows us, among many things, is something crucial about the difference between knowing that something is wrong and knowing where the wrongness is. C. elegans has neurons dedicated to detecting specific kinds of harmful stimuli. Harsh touch in different body regions activates different neurons. Noxious heat activates a different pathway than noxious chemicals. The worm does not just detect damage in general. It detects this kind of damage. Here, now, at this location on my body. This is not a small distinction. This is the difference between an alarm that says something is wrong and an alarm that says the kitchen is on fire. Think about what that specificity makes possible. An alarm that says something is wrong can only generate one kind of response. Stop, freeze, wait, do something, anything different from what you were doing. But an alarm that says the threat is coming from behind and to the left, that it is mechanical pressure rather than heat or chemical, that it is severe rather than mild. That alarm can generate a response calibrated to the actual situation. Move forward, move fast, protect this specific part of the body while keeping the rest functional. The more specific the warning, the more useful it is. And usefulness, in the Cambrian and post-Cambrian oceans, translated directly into survival. The animal with a more precise map of its own damage was the animal that could respond more precisely to the thing causing that damage, which meant it was more likely to escape with enough of itself intact to reproduce. To survive, a body had to learn not only that something was wrong, but where the wrongness was. C. elegans also shows us something else, something that hints at where this story is going, though the worm itself is nowhere near the destination. After exposure to a harmful stimulus, C. elegans becomes more sensitive to similar stimuli. Touch a region that has been recently stressed, and the response threshold drops. The worm reacts more strongly, more quickly, to less provocation. Its nervous system has changed, at the level of the synapses, based on what happened to it. This is called sensitization, and it is one of the most important things a warning system can do. Because a warning system that treats every potential threat identically, regardless of history, is a warning system that cannot learn. If your alarm goes off just as loudly for a familiar, safe stimulus as it does for the thing that damaged you last week, the alarm is producing noise rather than information. But if your nervous system can adjust its sensitivity based on past experience, if the place that was hurt becomes a place that is monitored more carefully, then the warning system is doing something more sophisticated than detecting. It is beginning to remember. Not remember in the way a human remembers. See, elegans has no episodic memory. It is not replaying the event that sensitized it or thinking about how to avoid a repeat. The change is molecular, structural, a shift in the chemistry of synaptic connections that makes the nervous system respond differently going forward. But the result is something functionally similar to what memory produces in more complex animals. The past is shaping the present. What happened to this body is influencing what this body does now, and that influence is running through the very hardware that detects damage and generates responses. The warning system is not just a sensor. It is a sensor that updates itself based on what it detects. This seems obvious. Stated plainly, of course, a useful warning system would adapt to what it encounters. But consider what it required to build this. Consider how many generations of animals that could not update their sensory thresholds based on experience were consumed by the things they failed to respond to adequately. Consider the selection pressure that produced, across lineage after lineage, nervous systems biased toward over-response after injury rather than under-response. The bias towards sensitization after damage is not an accident. It is one of the most consistent features of nervous systems across the entire animal kingdom. Humans have it. Mice have it. Flies have it. C. elegans has it. The molecular mechanisms differ, but the functional result is the same. An injury makes the injured region more sensitive. The warning system turns up its own volume in the place it has reason to monitor closely. This makes biological sense so obvious it is almost easy to miss. If something damaged you here is where you need to be most careful. Here is where the next threat might come from. Here is where a small problem could become a large one if it is not caught early. Turn up the sensitivity. Listen harder. Do not let what happened here happen again without noticing. The map of damage is not just a record of what has been hurt. It is an ongoing adjustment of how carefully different parts of the body are being watched. You carry this map right now. Every scar on your body, every place that was once seriously injured, is a place where your nervous system learned to pay closer attention. The sensitivity may have faded. The injury may have long since healed. But the architecture that registered the damage, that updated in response to it, that learned to monitor that region more carefully, that architecture does not simply reset to zero when the wound closes. The body does not entirely forget where it has been hurt. In chi, elegans. This is a molecular adjustment with no experiential dimension we can identify. 302 neurons. Doing what 302 neurons do, without any indication that anything it is doing involves anything we would recognize as feeling. But the logic is there. The functional logic that will, given a sufficiently complex nervous system and a sufficiently integrated brain, eventually produce something that does involve feeling. Something happened to me here. Something might happen again. Watch more carefully. That is not yet pain as humans know it. It is not yet suffering. It is not yet memory in any rich sense. But it is the beginning of the idea that what happened to a body in the past should influence how that body behaves in the future. That injury is not just a present tense problem, but a piece of information about what the future might hold. And once a nervous system begins operating on that logic, something has shifted. The warning is no longer only about right now. It has started reaching, however clumsily, toward then. There is a sea slug that changed what we know about memory. It is not beautiful, as sea creatures go. Aplysia californica is large, soft, brownish. Not the kind of animal that ends up in nature, documentaries about the wonder of ocean life. It has no particular grace. It moves slowly across the seafloor, grazing on algae, doing very little that would capture anyone's attention. But Aplysia has something that made it invaluable to science. It has neurons large enough to see with the naked eye, large enough to insert an electrode into with reasonable precision, large enough to watch, in real time, what happens inside a single nerve cell when an animal learns something. Eric Kandel spent decades watching those neurons. He won the Nobel Prize in Physiology or Medicine in the year 2000 for what he found. And what he found was this. When Aplysia is touched on its gill in a way that startles it, it retracts the gill, a simple protective reflex. The kind of response a nervous system with very little complexity can produce. Touch here, withdraw there. Signal travels. Muscle contracts. Body protects itself. But if you pair that touch with a painful stimulus to the tail, something changes. Not just in the behavior, in the cells themselves. The neurons that carry the signal from touch to withdrawal become more excitable. Their connections to the motor neurons that drive the response become stronger. The molecular machinery inside the cells physically changes. New proteins are synthesized. Synapses are restructured. The animal does not just react differently. It has been altered at the level of its biology by what happened to it. And the result is a nervous system that responds more strongly, more quickly, and for a longer duration to stimuli that previously would have produced only a mild reaction. Aplysia has been sensitized, not through thought, not through reasoning, not through anything resembling conscious recollection, through the direct physical remodeling of its own neural connections. The past has been written into the hardware. This is what memory looks like at its most fundamental level. Not a story the brain tells itself. Not a replay of events. A change in the physical architecture of the nervous system that makes the organism different. In its responses, and its thresholds, and its behavior, because of something that happened to it before. And what Kandel showed, in work that has held up across decades of subsequent research, is that the molecular mechanisms underlying this kind of learning are not unique to Aplysia. They are conserved across species separated by hundreds of millions of years of evolution. The basic chemistry of how a nervous system changes itself in response to experience is recognizably the same. The details differ. The scale differs. The complexity differs enormously. But the underlying logic, experience changes the hardware changes the response, is one of the most ancient features of nervous systems that we know of. Pain became powerful when it stopped being only a moment and became a memory. Think about what this means for survival. An animal that can only respond to damage in the present tense, that reacts to what is hurting it right now, but whose nervous system resets completely between encounters. That animal is at a permanent disadvantage compared to an animal whose nervous system retains some trace of past damage. Not because memory is philosophically important, because memory is strategically important, because the place that was damaged before is likely to be a place where damage could happen again, because the stimulus that preceded the injury is a signal worth responding to before the injury repeats. The animal that remembers, even in the purely molecular sense that Aplysia remembers, is an animal that is learning from pain, rather than merely experiencing it. And learning from pain means that pain is doing more than protecting the body in the moment of injury. It is shaping the animal's behavior going forward. It is reaching from the past into the future. It is turning a single event into an influence that extends across time. Now consider the crab. Experiments on shore crabs have shown something that goes a step further than Aplesia's sensitization. Crabs placed in a brightly lit area, which they naturally avoid because it increases their vulnerability to predators, can be given a mild electric shock. They learn to avoid the lit area more strongly. So far, this might just be another version of sensitization. But here is where it becomes interesting. If you give those crabs a shelter to hide in when they are in the lit area, and then remove the shelter, the crabs that have been shocked will work harder to find a hiding place and will be more likely to leave the lit area entirely. They are not just reacting to a current stimulus. They are making trade-offs based on past experience. The memory of the shock is influencing a decision about risk. This does not prove that a crab suffers the way a human does. The distinction is important, and the science is honest about it. But it shows something more than a simple reflex. It shows behavior shaped by past injury, an organism adjusting its choices, its priorities, its willingness to accept certain risks based on something that happened to it before. The memory of damage is influencing the future. That is a remarkable thing. It is also, when you think about it, the beginning of something that will eventually become one of the most defining features of human experience, because the ability to let past pain influence future behavior is the same ability that, given a sufficiently complex nervous system, will eventually allow an animal to anticipate pain, to dread it before it arrives, to be shaped not just by injuries that have happened, but by injuries that might happen. The warning system is no longer limited to the present. It is beginning to reach backward into the past and forward into the future simultaneously. And an animal that can do that is an animal that is starting to live in time in a way that simpler nervous systems cannot. Not yet consciously, not yet with the richness of human temporal experience, but functionally, behaviorally, in ways that influence what it does and how it moves through the world. There is something worth pausing on here. Before we go further, we tend to think of memory as one of the gifts of complex minds, something that comes with intelligence, with language, with the sophisticated neural machinery of vertebrate brains. And it is true that human memory is extraordinarily elaborate. We can remember specific events from decades ago. We can remember the smell of a place we visited once as a child. We can remember, in sometimes painful detail, things we would rather forget. But the basic function of memory, allowing the past to shape the present, allowing experience to change behavior, is not a feature of complex minds. It is a feature of nervous systems at a very early stage of their development. Aplysia has it. Crabs have some version of it. C. elegans has a molecular version of it. The machinery of learning from damage is one of the oldest things nervous systems do. What changes as nervous systems become more complex is not the basic function. It is the depth and richness and reach of that function. The past that influences the present becomes longer, more detailed, more precisely encoded. The future that past experience is allowed to shape becomes more distant, more elaborately modeled. The animal that can carry a week-old injury forward as a behavioral influence becomes an animal that can carry a year-old injury forward, then a decade, then a lifetime. And at some point along that continuum, something happens that the story has been building toward since the very beginning. The memory of pain stops being only a biological adjustment. It becomes something an animal lives with, something it carries, something that is not just shaping its responses from the outside, like a modified synapse, but something that exists as part of what it means to be that animal moving through the world. When exactly that happens, the science cannot say with precision. There is no fossil record for the moment when stored damage became felt memory. There is no molecular marker that distinguishes neurological adjustment from genuine subjective experience. But something changed. Somewhere in the long history of nervous systems becoming more integrated, more centralized, more capable of holding the past and projecting into the future, the warning system crossed a line, and on the other side of that line, pain was no longer just something a body detected. It was something a creature experienced. Here is a question science has not answered. Not because it has not tried, because the tools for answering it do not yet exist in a complete form. At what point does a nervous system stop processing signals and start feeling them? The question sounds like philosophy. It is actually the most concrete problem in the biology of pain, and it sits at the center of some of the most serious scientific debates of the past 30 years. Because if we cannot answer it, we cannot know which animals suffer. We cannot know where, in the history of life, suffering began. We cannot know, with any precision, what we are talking about when we talk about pain in any creature other than ourselves. What we can do is look at behavior, and when we look at behavior, some animals make the question very difficult to dismiss. The octopus is the hardest case. An octopus has approximately 500 million neurons. That is more than a rat. The majority of those neurons are not in its central brain, but distributed throughout its arms. Each arm capable of independent processing and action. The octopus can solve novel problems it has never encountered. It can learn by watching other octopuses. It can recognize individual human faces. It uses tools. It plays, in the sense of repeatedly engaging with objects in ways that produce no apparent survival benefit, but that, it appears, for lack of a better word, to enjoy. When an octopus is injured, it does not simply withdraw from the stimulus and reset. It guards the injury. It changes its behavior in ways specifically organized around protecting the damaged area. It makes trade-offs. Given a choice between food in a location that requires using an injured arm and food in a location that does not, it adjusts its behavior accordingly. The wound is not just a site of nociception. It is a site of ongoing concern. The animal's attention returns to it. Its choices organize around it. The United Kingdom's Animal Welfare Sentience Act of 2022 explicitly recognized cephalopods, including octopuses, as sentient beings. This was not a sentimental gesture. It was a policy response to a substantial body of scientific evidence evaluated by an independent panel of researchers. The evidence did not prove that an octopus suffers exactly as a human suffers. It showed that the behavioral and neurological complexity of these animals was sufficient to take seriously the possibility that they experience something. The octopus does not answer the question. It makes the question impossible to dismiss. And that is actually the most scientifically honest position available. Because the mystery is not when bodies began to react. We know when bodies began to react. The mystery is when reaction became experience. To understand why that question is so hard, it helps to think about what experience actually requires. At minimum, experience seems to require integration. Not just signals traveling through a nervous system, but signals being brought together somewhere, compared, weighted, given a unified significance. A nerve net, like hydras, distributes processing across the whole body and produces coordinated responses. But there is no convergence point, no place where all the signals meet and become a single, unified state of the organism. As nervous systems evolved, central processing regions, as brains developed, something changed about the nature of what those systems could do. Not just faster signaling or more precise localization. The possibility of a unified inner state, a condition of the whole organism, rather than a collection of local responses that the organism is in. What does it feel like to be an octopus? We genuinely do not know. We may never know with certainty. The problem of accessing another creature's subjective experience is one that philosophy has wrestled with for centuries and biology has no clean solution to. But consider this: to feel pain in the full sense, a body must be integrated enough to register damage not just locally, but globally. The injury must matter to the whole organism, not just to the cells at the site of damage. And for something to matter to a whole organism, there must be something it is like to be that organism. There must be, in some functional sense, a perspective, a point of view from which the damage is registered as bad, as something to be avoided and escaped, not just as a signal to be processed and responded to. This does not require language. It does not require self-reflection in the philosophical sense. It requires something more basic and more ancient. Sufficient integration for damage, to feel like damage rather than just being processed as damage. And here is what makes the history of nervous systems so important to this question. The more centralized a nervous system becomes, the more integrated its processing, the more possible it becomes that signals from different parts of the body are being brought together into something like a unified state, not just parallel processing happening in parallel, but convergent processing, producing a single condition of the organism. In creatures with complex, centralized brains, there is no serious scientific debate about whether they experience pain. The mammalian pain system is well understood. The regions of the brain that process pain signals overlap extensively with regions involved in attention, emotion, memory, and decision-making. Pain in mammals is not a separate channel running alongside experience. It is woven into experience. It colors everything else. It demands attention. It interrupts ongoing behavior. It persists after the initial stimulus is gone, because the brain regions processing it are the same regions that sustain states across time. When you burn your hand and the pain keeps coming even after you have moved away from the heat, that is not a malfunction. That is the integrated pain system doing exactly what it evolved to do, making sure the damage is not ignored, making sure the attention of the whole organism stays on the problem until the problem is resolved. But here is where the history meets the present, in a way that changes how you think about pain. The architecture that produces this integrated experience was not built all at once. It was assembled over hundreds of millions of years, one layer at a time. The oldest parts of the human pain system are the oldest parts of the vertebrate pain system. The pathways that carry nociceptive signals from the periphery to the spinal cord and up to the brain are ancient. The molecular machinery of nociception, the specific proteins that detect heat and pressure and chemical damage, are conserved across species, separated by enormous evolutionary distances. You are running ancient software on a modern system. The warning hardware was built for a Cambrian ocean, for immediate threats, short durations, damage that was either survived quickly or not survived at all. The signal was supposed to arrive, mobilize a response, and clear when the threat was gone. but in a brain with memory, with anticipation, with a sense of self that persists across time. The signal does not always clear, and that is where the story turns. Not toward failure, not toward a flaw in the design, toward something more interesting and more tragic than either of those framings allows. Toward what happens when a warning system built for simplicity has to operate inside a mind built for everything else. She was born in 2004 in a small town in Pakistan. By the time researchers encountered her case, she was a young teenager who had spent her entire life without feeling a single moment of physical pain. She had walked on a broken ankle for 3 days before anyone realized it was broken. Not because she was brave, because she had no signal telling her anything was wrong. She had bitten through the tip of her tongue as a young child. While eating, she had placed her hands on a hot stove, not in defiance of pain, but in the complete absence of any reason not to. Her case was published in a medical journal and became one of the most referenced examples of a rare genetic condition called congenital insensitivity to pain. The gene involved codes for a protein in the membranes of nociceptive neurons. Without it, those neurons cannot fire properly. The signals that should travel from damaged tissue through the spinal cord and into the brain simply do not arrive. She could feel touch. She could feel temperature in a limited way. She was not numb, but pain, as a signal, as an alarm, as the body's most urgent form of communication, was unavailable to her. And the damage accumulated in ways that are hard to read about. Her joints were deteriorating in her early teenage years from repeated stress injuries she had never felt any reason to avoid. Her skin carried scars from injuries that had gone unprotected and unnoticed long enough to become serious. Every day of her life, her body was sustaining the kind of ordinary damage that normal nervous systems flag immediately and protect against instinctively. And none of it was being flagged. The danger is not that people like her are fragile. The danger is that their bodies cannot warn them when they are being damaged. Pain does not just announce injury. It enforces rest. It makes you guard the wounded area. Keep it still. Keep it clean. Keep it protected while it heals. It makes you change how you move to avoid putting stress on something that is not ready to bear stress. It makes you remember, viscerally and immediately, not to repeat the action that caused the damage. Without pain, none of that enforcement happens automatically. Every protection that a pain provides has to be substituted by conscious attention. Every moment of every day, without the benefit of an alarm that goes off when attention lapses. It is exhausting in a way that is almost impossible to communicate to someone whose nervous system handles all of that automatically. The absence of pain is not freedom. It is silence where an alarm should be ringing. And in that silence, the body quietly accumulates what it cannot report. Now, consider the opposite direction. Consider what pain does when it works exactly as intended. You sprain your ankle. The pain is immediate and significant. It stops you from walking on it. It makes you favor the injured leg. It makes you rest, elevate, protect for the next several days. Every time you accidentally load that ankle with weight, the pain spikes and reminds you to stop. The pain is not punishing you. It is enforcing the conditions that healing requires. It is doing the work that your conscious attention, distracted by the rest of your life, cannot do consistently on its own. You touch a hot surface. The withdrawal reflex happens before you are aware of it, as we established at the very beginning of this story. But then the pain continues, not because your hand is still in danger, but because your hand is damaged and needs to be treated as such. The pain keeps your attention on the injury. it makes you hold the hand carefully. It makes you seek cooling, relief, treatment. It makes you tell other people what happened so they do not touch the same surface. Pain is social as well as individual. In species that live in groups, the expression of pain communicates information to others about dangers in the shared environment. The warning system is not only protecting you in a social species, it is protecting the group. And then there is the deepest layer of what pain does, the one that becomes visible only when you look at it across evolutionary time. Pain is one of the primary ways an animal learns what the world will and will not allow. Children learning to navigate the physical world do so partly through pain, not because pain is a good teacher in any warm sense of that phrase, but because pain is an honest one. It does not give incomplete information. It does not allow the lesson to be deferred indefinitely. When a child learns that a certain action produces pain, that lesson is encoded with a biological emphasis that conscious instruction cannot easily replicate. The nervous system marks the experience as important. Memory systems that prioritize emotionally significant events hold on to it. The child's future behavior changes not because someone explained the danger, but because the danger explained itself. This is a brutal way to learn. It is also extraordinarily effective. Every animal that navigates a complex and dangerous world does so partly on the basis of an accumulated personal history of what hurt and what did not. That history is not stored as a list of facts. It is stored as a set of biases, sensitivities, aversions, and preferences built into the nervous system itself, shaping behavior from the inside without requiring conscious consultation. The warning system, in other words, is also an education system, and the education it provides is the most direct possible. The world itself is the teacher. The lesson is pain, and the consequence of not learning the lesson is the repetition of the injury. This is the gift, not a comfortable gift, not a gift anyone would choose if the alternative were available, but a gift in the most fundamental biological sense, a system that keeps you alive by making certain things unbearable, a system that enforces behaviors your survival depends on, without requiring your conscious cooperation, without asking your permission, without giving you the option to decide it is not worth attending to right now. Evolution does not design for comfort. It preserves systems that worked well enough, often enough. In the environments where they evolved, the pain system worked. Across hundreds of millions of years and thousands of species, animals with more sophisticated pain systems survived and reproduced at rates that outpaced animals with less sophisticated ones. The system was retained, refined, elaborated, and passed forward because it was effective. The animals that felt pain stayed alive long enough to pass on the nervous systems that made them feel pain. And this is where the story reaches its central paradox, because the same logic that made the pain system so effective is also the logic that makes it capable of becoming a source of profound suffering, a system biased toward over-response rather than under-response. Because missing real damage is more dangerous than responding to a false alarm. We'll sometimes respond when there is nothing to respond to. A system that writes past injury into the nervous system as a lasting change in sensitivity will sometimes maintain that sensitivity long after the original injury has healed. A system that allows pain to influence memory and decision-making, and the animal's model of what the world is likely to do to it, will sometimes allow pain to influence all of those things in ways that go far beyond what any current threat requires. These are not failures. They are the predictable consequences of a system calibrated for a world where the cost of under-response is death. In a world of immediate threats, short encounters, injuries that either killed you quickly or healed quickly. That calibration was close to optimal. In the world that humans now inhabit, a world of chronic conditions and complex social stresses and injuries that the medical system can heal, but the nervous system has not yet been informed of. That same calibration can become something very different from a gift. The warning system does not know that the world has changed. It is still running the ancient calculation, still biased towards sensitivity, still writing injury into its own architecture as a lasting adjustment, still reaching from past damage into present behavior and future anticipation, still doing, with absolute biological fidelity, exactly what it was built to do. And in some people, in some conditions, that fidelity is what destroys them. In the 1980s, a neuroscientist named Vilayanur Ramachandran began working with patients who had lost limbs and were experiencing something that medicine had not yet adequately explained. They felt pain in the missing limb, not metaphorically, not as a psychological response to grief or loss, as a physical sensation, specific and located, in a hand that was no longer attached to their body, in a foot that had been amputated years before. The pain was real in every sense that mattered to the person experiencing it. It kept them awake. It interrupted their thoughts. It did not respond to treatments aimed at the site of amputation because there was no site. The tissue was gone. The nerve endings at the residual limb were not the source. The source was the brain. Ramachandran understood that the brain maintains a map of the body, not a map stored in one place, but a distributed representation, built up over a lifetime of sensory experience, that encodes where every part of the body is and what it feels like and how it relates to every other part. This map is not a passive record. It is an active model that the brain uses to interpret incoming signals and generate predictions about what the body is experiencing. When a limb is amputated, the signals from that limb stop arriving, but the map does not immediately update. The regions of the brain that represented the missing hand, the missing foot, the missing arm, are still there. They are still organized to process signals from a body part that no longer exists. And in the absence of normal input, those regions can generate their own activity. They can produce the experience of sensation in a limb that is not there. They can produce the experience of pain in a limb that is not there. Phantom limb pain was not, before Ramachandran's work and the work of others who followed, well understood as a phenomenon of the brain rather than the peripheral nervous system. It was often dismissed, misunderstood, treated at the wrong level. His insight that the map could outlive the territory changed how the field understood not just phantom pain, but pain in general. Because phantom limb pain is not an anomaly. It is the pain system behaving exactly as it was designed to behave, in a situation the design never anticipated. The map was built on the assumption that the body would persist, that the signals it was calibrated to interpret would keep arriving, that maintaining a detailed representation of a living limb was always worth the neural resources it required, because the limb would always be there to benefit from that representation. The limb is gone. The map remains. The alarm system, still watching a territory that no longer exists, still generating alerts that the absent territory is in distress. This is not a malfunction. This is the pain system doing its job in a context where its job has become impossible. Now extend this logic, because phantom limb pain, dramatic as it is only one expression of a much broader phenomenon. Chronic pain affects an enormous number of people worldwide. Pain that persists for months or years after the original injury has healed. Pain that exists without any identifiable ongoing tissue damage. Pain that does not respond to treatments targeted at peripheral sources, because the peripheral sources are no longer the problem. What has happened in many cases of chronic pain is that the nervous system itself has changed. The sensitization that is useful and appropriate in the short term, the turning up of the alarm's sensitivity in the immediate aftermath of injury, has persisted and generalized. The pathways that carry pain signals have become more excitable over time rather than less. The threshold for generating a pain response has dropped. The brain regions that process pain have reorganized around the experience of chronic pain in ways that make the pain self-sustaining. The alarm has become the emergency. Evolution does not design for comfort. It preserves systems that worked well enough, often enough, in the environments where they evolved. A warning system biased toward over-response rather than under-response made sense in a world where the consequences of missing real damage were immediate and severe. The cost of false alarms, of sensitivity that persisted longer than necessary, was manageable when the baseline threats were the kinds of threats the Cambrian Ocean produced. Injury happened. Recovery was quick, or death was quick. The nervous system reset, or the animal did not survive to require resetting. In modern humans, that same bias can become devastating. A system built to protect the body can keep protecting long after protection is no longer the right response. It can keep escalating sensitivity in a nervous system that has not been given the signal that the threat is over. It can recruit memory, attention, emotion, anticipation, all the sophisticated machinery of the human brain, into the service of an alarm that is responding to a threat that no longer exists in the form it is treating it as existing. And here is the part that is perhaps hardest to sit with. The human brain does not just process pain. It anticipates pain. It remembers pain. It models pain. It can generate the experience of pain, not just in response to current tissue damage, but in response to the expectation of tissue damage, to memories of past pain, to situations associated with previous pain, to the thought of pain. In a context where pain seems likely, this is not weakness. This is the predictive machinery of a sophisticated brain applying itself to the problem of pain. The same way it applies itself to every other problem it is responsible for managing. The brain that can anticipate a threat and generate a preparatory response is the brain that does not have to wait to be hurt before it starts protecting. The brain that remembers pain vividly and allows that memory to influence current behavior is the brain that learns most effectively from experience. These are features. They are the result of the same evolutionary logic that produced the pain system in the first place, applied at a higher level of complexity. But features become liabilities when the environment they were designed for no longer matches the environment they are operating in. A brain that can generate pain in response to expectation can generate pain in a person who is afraid of re-injury, even when no re-injury is occurring. A brain that ties pain memories to contextual cues can generate pain responses in environments that were associated with past pain, even when the original cause is gone. A brain that models the body's state based on accumulated experience can model that state incorrectly, in ways that generate ongoing pain signals that do not correspond to any current tissue damage. The warning system has been absorbed into the larger predictive machinery of the brain. And the larger predictive machinery of the brain, powerful and plastic and capable of extraordinary things, is also capable of sustaining states that have no current justification in the body's actual condition. Pain began as a message from the body. In humans, the message can outlive the wound. It can outlive the body part. It can outlive the event that started it, and it can recruit every sophisticated capacity of the human mind into keeping itself alive. This is not a flaw in the system. This is what the system becomes when complexity has no ceiling. The same architecture that allowed nervous systems to protect bodies in the Cambrian Ocean, refined and elaborated over hundreds of millions of years, connected to memory and emotion and anticipation and self-model and language and identity, is the architecture that makes chronic suffering possible in a way that no simpler nervous system could sustain. You cannot have one without the risk of the other. The warning and the wound are built from the same materials, and understanding that does not make the pain less real, but it does make it something other than a mystery. It makes it the predictable consequence of a system doing its job. In a world far more complex than the job was originally designed for, the alarm is not broken. It is running perfectly. In a building whose architecture has changed so completely around it that perfect is no longer the same as useful, the warning system is still running. Right now, as you read this, it is monitoring the boundary between the world and you, checking, adjusting, doing the ancient work it has always done. The work that began in soft bodies pressed against seafloor sediment long before anything alive had a name for what was happening to it. You inherited this from every animal that survived long enough to pass it on. From Dickinsonia, which almost certainly had no system at all for turning damage into information. From the nerve nets of cnidarians that first let one part of a body tell every other part that something had touched it. From the organized nociceptive pathways of Cambrian animals whose nervous architecture we can read in stone. From Aplysia, whose synapses were physically rewritten by experience. From the octopus guarding its wound in a way that made a question impossible to dismiss. Each of those animals passed something forward. Not intentionally, not with any awareness that a chain was being built. Just by surviving long enough to reproduce, carrying the hardware that helped them survive into the next generation, where it was refined, elaborated, connected to more and more of what the organism did and felt and chose, until it arrived here, in a species that can hold the entire history of that system in its mind and ask what it means. The same architecture that built the reflex, built the memory. The same system that pulls your hand from fire is the system that wakes you at 3 in the morning with something that happened years ago. The same integration that makes joy possible makes grief possible. The same predictive machinery that lets you anticipate pleasure, lets you anticipate pain. You cannot have one without the other. That is not a flaw. That is what the gift costs. Silas Weir Mitchell sat beside soldiers who were describing pain in limbs that were gone. And he believed them when no one else did. Because he understood that the body was reporting something real. Not from the wound. From the map that outlived the wound. The map is still there. It has always been there. And the fact that you can hold this entire story in your mind, from the first nerve net to the last unanswerable question, that is the map doing something Mitchell could not have predicted, making the wound capable of understanding itself.